So we have been learning Newton's laws of motion, and we have actually got a fairly good introduction with them. Now we try to apply those laws to 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 get a better understanding, because the Newton's laws are deceptively simple. When you look at the equations and look at the definitions, they are very simple. But when you apply it to different situations, depending on how complex the situation is, it becomes very difficult to keep traction of things. That's why the only way to master the Newton's laws, well, not just the definitions are very easy to remember, but mastery in the sense that you are able to apply to very complex, difficult actual situations and be able to solve them, be able to find the answers that you are looking for. So we would consider a few examples of applying Newton's laws. So, and I'll explain you a scheme as well, how to solve problems when you have a situation, when you have different situations. So for example, let's say that we have an object a block, let's say, is dropping, has a certain mass m. Okay, how many forces are acting on this block? Just one force, right? The force of gravity. It's in free fall. There is no other force acting on this block. So only one force is acting on this block. But now let's say that this block is resting on a flat horizontal surface. Okay. So now how many forces are acting on this block? So let's make a free body diagram. There is the force of gravity that is acting on this object. It is simply mass times the gravitational acceleration near the surface of Earth, mg. And this force is acting downwards. And the normal force that this horizontal surface is exerting on the block. Okay. And we call it a normal force because it makes a 90 degrees angle. The force makes a 90 degrees angle with the surface that is exerting that force. So the force is always normal to the surface. Only two forces now are acting on this object. So this is how you solve a problem. You look at the problem, you identify the body that you are interested in, the object that you are interested in, and then you take into account all the forces that are acting on it, and then you try to expand this general expression of the Newton's second law. Okay, sum of all forces acting on in single object on an object is equal to mass times the acceleration of the object. Okay, so this is a vector equation. Let's say that we have a frame of reference that y is upwards and x is in this direction. Okay. If you look at this object, there is no force acting in the x direction, and the object is at rest. Okay, that means only the forces that are acting are in the y direction. So I can write, for example, the normal force positive because it's in the positive y-axis, the weight or the force of gravity. So this is the sum of, this is the left side of the upper equation upstairs, equals m a y, the acceleration in the y direction. So I'm writing a equation for just the y component of this equation. You can also write this equation like this. If you want to be more precise, you can write even better like this. E unit vector. So minus mg unit vector y equals m a sub y a unit vector y. All right. So then comes the physical condition that we are imposing. So we are already saying that this block is not moving, is at rest in neither direction, nor in the x nor in the y. So that means ay is 0. Now if you plug that in, what you would get is n equals mg. Right? The normal force is equal to the weight of the object. But I must warn you that this is a special case. This is not always true. This is a special case that the normal force is equal to the weight of the object. This is not always true, and we will see more examples where we would realize this. So now let's consider another example. So let's say that we have an accelerator, an elevator, okay, and it's accelerating upwards. And then we have a block sitting at the floor of the elevator. All right. And now we try to analyze the forces acting on the block. Okay. So one of the force that is acting on the block is, we can again make a free body diagram. One of the force acting on the block, of course, is the mass, the weight of the block downwards. Okay. Then, since the block is resting at the floor of the elevator, so there is a normal force acting in this direction. Is there any other force that is acting on this block? No other force is acting on this block. So again, we expand this equation here, right? And we choose the same coordinate system, y pointing upwards, x on the right side. So Ey plus n y unit vector. Okay. The two forces, all the forces on the left side and on the right side, mass times the acceleration of the block. Since the block is not moving with respect to the elevator, so it has the same acceleration as the elevator. And let's say that the acceleration of the elevator is a particular value, capital A. Okay. Since all the forces are in the y direction, I can just simply drop the unit vectors and work with scalars. And that's also perfectly fine. So this is mg plus n equals ma. And now the normal force turns out to be ma plus mg. So here is an example where normal force is not equal to the weight. Now normal force is it larger than the weight or smaller than the weight? Anyone?
So it's larger.
Smaller.
Larger.
Why smaller? Let me say it more clearly. The elevator is accelerating upwards and the acceleration is positive in our coordinate system. Then
तो सर कॉन्टैक्ट फोर्स पे लार्जर है ना वेट से, मेरे ख्याल से वेट से, क्योंकि MA प्लस MG है N के लिए.
So that's what I'm asking, that is N larger than the weight of the normal force, larger than the weight of the object, or equal to, or smaller than?
Larger, I think.
Larger, yes, very good, yes. So now the normal force is larger than the weight of the object. So this is another example elaborating that generally normal force is not equal to the weight. It's a common misconception. Another way to distinguish between or to draw another conclusion is that the normal force really depends on the situation that you're in. Okay, the weight always remains constant near the surface of Earth. I mean, once you decide what object you're talking about, in a way you have fixed the mass, and the gravitational acceleration near the surface of Earth is constant, is approximately 10 meters per second per second. So this is nearly constant near the surface of Earth. Okay, the normal force, depending on the situation, in this situation that we had here, normal force is simply equal to the weight of the object. Here it is larger than the weight of the object, because the normal force not only has to sustain the weight of the object, but it also has to support or provide counter the extra acceleration that the elevator is accelerating. The elevator is going upward, so it has to push or to account for this term as well. Okay. Another example of normal force. So let's say you have an object sitting on a horizontal surface, not accelerating. In just the previous example, we have seen that normal force in this case is equal to mg. But let's say I start pushing it. Okay, we push it from upwards by hand. Let's say I put something like this duster here, and then I push it. Okay, let's say I push it with 10 Newton force. Okay, what would be the normal force then? Mg plus 10 newtons, no? Because the normal force would be equal to all the forces that are acting, would oppose all the forces that are acting on the block, or then acting on the on the surface. Okay, so if I keep increasing the push, you see this equation here, mg plus whatever the value of the push force that I am pushing would keep changing. So if I change the push, it would change the normal force. Is there an upper limit how large the normal force can be?
नहीं सर, until unless आपकी जो surface है वो बहुत weak है और टूट सकती है, like a tabletop or something.
Yes. So the strength of the tabletop is basically the upper limit. Okay. As long as the structure sustains, okay, I can keep applying larger and larger force, but at some point, if it is a solid structure, a man-made structure, it has everything has a breaking limit. Okay, and the structure is held together by electrostatic forces. Again, the origin of the normal force microscopically it comes from the electrostatic forces between the constituent particles of the surface. Okay. So, and another example, another interesting way to think about it is that when you walk, you feel your own weight on your legs, right? And what you're feeling is not really your weight. It is the normal force that Earth is exerting on your body. That is what you feel, okay? And let me explain it. So if you're just standing stationary on the surface of Earth, the normal force exerted by Earth on your body, and again, even when the normal force is equal to the weight, please be careful. this means that the normal force is equal to the weight in magnitude only. Both forces are acting in two opposite directions. Okay, normal force is acting on upwards on the body, and the weight is acting downwards on the body. Okay, so in normal situation, the normal force acting on your body is just your weight. Okay, and what you feel is your weight. But to make this point that it's not actually your weight that you're feeling, is the normal force that Earth is exerting on you, is, let's say that you are now in an elevator. Okay. You're standing in an elevator which is accelerating upwards with an acceleration A. Okay. And like previously, now the normal force acting on you would be your weight plus mass times the acceleration of the elevator in which you're standing. Okay, and that is why when the elevator accelerates upwards, today's elevators are very good, so they accelerate very slowly in a way that you don't really feel it. But if you are in a bad in a bad elevator which accelerates quite quickly, so what you feel is you feel this acceleration. Okay, and you feel a little heavier, and that is because your weight hasn't changed. It is just the elevator which is accelerating, and you feel a little heavier. Now consider the opposite situation. Let's say now the elevator is descending and is accelerating downwards. The normal force would be mg minus ma. And when an elevator accelerates downwards, you feel a little lighter. Okay, your weight hasn't changed. It's the normal force which has changed. All right. And now imagine what happens when the elevator is descending and accelerating with the acceleration of g, or 10 meters per second squared. What happens then?
Yes.
Mg, and the normal force acting on you is 0. Okay, you become weightless. Your weight hasn't gone to 0. Okay, well, it has in a way in your frame of reference, but it's actually the normal force that has gone to 0. Okay, and this is what is called weightlessness. Okay, now some techniques for solving the problem. Okay, again, I'll just consider the same example that we are looking at, or we could just consider an inclined plane. Okay, and then we have a block sitting here. Okay, probably moving. All right. So the general scheme is that whenever you have to solve a problem, first very carefully pick the body that you are studying. Is it the block? Is it the inclined plane? Or is it something else? Or maybe there is another block here or something else, or maybe another block sitting on top of this block. You can have various situations. Carefully pick which object you are studying. Okay, that's the first rule. Which body that you are going to look at. The first rule, the starting point. Once you have chosen which object you are studying, let's say you are studying this object, okay, this one, the bigger block. Okay. Then draw a free body diagram. A free body diagram is that you remove its environment and replace all the interaction with the environment by the forces exerted by the environment on that object. Okay. That is what free body diagram means. You take this object, you remove its environment and replace any interaction that the environment has with the object by the forces, by the corresponding forces So what forces are acting on this object? One of them is, again, the weight. Okay. The normal force. Now, normal force would be in this direction. Okay. The normal force. Let's say we haven't really started using friction, but let's say there was a force of friction acting on this object. Fs. There are more forces. The smaller block is exerting forces on it. But the point is, the third point is, list all your forces. Okay. Do not forget any forces acting on your object. Do not invent any forces. Do not add any force that does not exist. And how to make sure that you do not miss any force? The trick is that in this course, there is only one non-contact force. There is only one non-contact force that can come from the object without being in contact remotely, and that is the gravitational pull. Okay. All other forces that we would be considering in this course are contact forces. So just analyzing the environment of the object, you should be able to identify all the forces that are acting on this object. Okay. It can be friction, it can be normal force, it can be a pull, another object, it could be weight of another object, for example, this mass of this smaller object acting on it. So everything, all other forces are contact forces. Okay, and you can decipher by looking at the environment. Okay, so again, I repeat, do not invent forces that they are not, which are not there. Do not miss any force, otherwise your answers would be, or your solution would be incorrect. Then choose carefully a coordinate system. Okay. Because without a coordinate system, vectors do not make sense, or it's difficult to work with them. Okay. So once you choose a coordinate system and an inertial one, an inertial coordinate system, once you have done that, then apply this vector equation, the Newton's second law. The vector sum of all the forces in your free body diagram on the left side and the acceleration on the right side. Okay. And very, very important point, the forces that you have that affect the motion of the object that you are interested in are the forces that are exerted by the environment on the body. Whatever forces this object exerts on its environment or other bodies do not affect its own motion. Do not include those forces, okay, in your calculation. Only the forces that are acting on this object by the environment, they affect its motion. So only those forces here and the acceleration of this object here. Usually, if you apply this whole scheme up to this point, you end up with more unknowns than equations, and you can't really solve it. So what usually you have is a constraint equation that helps you simplify your equation or helps you reduce the number of unknowns in your system. All right. So what is the constraint equation in this case? Let me just give you the constraint equation in this case, a simpler case. The constraint equation is, if this is x and if this is y, okay, the acceleration in x is 0. The object is not moving, is given, it's at rest. The acceleration in ay is also 0. So now I got two constraint equations for this system. Okay. In a similar way, if I carefully choose the coordinate system, and you will see we would do that. Let's say that we choose the coordinate system in such a way that this is my Ex, the unit vector, and Y is along the normal force, Ey. Then your constraint equation would be, and I chose this coordinate system to make the constraint equation simpler, that Ay in this case would be 0, no acceleration along the normal force. Okay. we imagine that this object keeps contact with the plane as it moves down. And we would have a non-zero acceleration. That's an unknown. Ax is now unknown. We will have to find what Ax is, the acceleration of the object along this surface, and the Ay is 0. So this is a constraint equation. So analyze the physical situation and deduce a constraint equation and then apply it to this system. Okay. Or simultaneously solve the constraint equation and the equation that you get from here for unknowns. And then finally analyze your results for sanity. Okay, that they should predict that the results should make physical sense. And I'll give you an example to explain what that means. Okay, so this is the basic scheme that you should be using while solving the problems. Any questions so far? So we continue with the example that we have to elaborate those points. Okay, so we have an inclined plane which makes an angle with the horizontal theta, right? And then we have a block. Sitting on this surface. Okay. First, the assumptions that we know the mass of the block is m. We also know that we ignore the force of friction. So Fs or Fk is 0. Okay, no friction. These are the assumptions or knowns of the problem. And the mass is equal to m. And then this block is the horizontal, the inclined plane is not moving, is there. Okay. And what we are interested in is we are interested in finding the acceleration of the block. All right. So the object that we are interested in is the block. And now we try to make its free body diagram. So it's free body diagram. And before we do that, let's choose a coordinate system. And we choose the coordinate system in such a way that this represents x-axis. X-axis is parallel to the inclined plane, and the y-axis is normal to the inclined plane. All right. Now we try to list all the forces. So there is the weight of the object acting downwards. There is normal force acting along normal to the surface of the inclined plane along y-axis. And if you ignore friction, there is no other force that is acting on this object. All right. So in our coordinate system now, the normal force is simple. So let's say it is just n EY. If you want to make a vector of it, the normal force. So how about weight? Now weight, so it's best to resolve it in the coordinate system so that we can work with its components. Okay. Now it's very easy to show. I hope that you have done this exercise, that if this angle is theta, then this angle is also theta. Okay. Now if you want to resolve this component, this would be the y component of weight, and this would be the X component of weight. I mean, it doesn't look parallel, but what I'm trying to do is to make a parallel to, sorry. And the Y component is simply mg cosine of theta. And the X component is simply mg sine of theta. All right. And now we try to write a vector equation. The sum of all forces and the acceleration. But it's best to just decompose this vector equation into its components and work with components. So now let's first start with the Y component. Okay. There is normal force in the positive Y direction, and then there is the weight, this component of weight here. Okay. And it's in the negative Y-axis. So minus mg cosine of theta equals m ay, and a unit vector here and a unit vector here. Okay.
Say MAY to 0 नहीं होएगा?
Yes, that's next thing that we need to do. Okay. So we have an equation for the Y component of the forces, or the equation, and then X component of the forces. Okay.
सर जो नॉर्मल होता है वो हमेशा वेट के ऑपोजिट होता है।
नहीं, देखें, ये तो वेट तो यहाँ इस तरफ एक्ट कर रहा है, तो वेट के अपोजिट तो नहीं है। वेट तो ऐसे एक्ट कर रहा है नीचे की तरफ, वेट के एक कंपोनेंट के अपोजिट है। ठीक है। सो AY, the acceleration in this direction, if we assume that it's sliding on this object and there are no bumps and there is no other force acting on this block, then just the acceleration in the Y direction is 0. We don't really need to solve this equation. Okay. And now the equation along X-axis, there is a positive force acting in this direction, and that is mg sine theta along the positive X-axis. Okay. Mg sine theta. Okay. So again, sum of all forces on the left side. Is there any other force on the left side? I mean, any other force acting along the X-axis? No other force. Okay. Equals MAX. And now you can just cancel M on both sides. Okay. And we have found the acceleration of the object. AX is equal to G sine theta and both components, and AY is 0. And the point of using this coordinate system in this particular way was that both the expression for the normal force is simpler, but then we had to resolve the weight. So if you choose the coordinate system in such a way that the weight is parallel to the negative Y-axis, then you will have to resolve the normal force. Okay, so there is no really shortcut here. So one way or the other, one expression becomes simpler and another becomes complicated. You will have to resolve it. And the advantage of choosing this is that we also got the simpler expression for the acceleration as well. Okay, so the acceleration is now along X-axis, parallel to X-axis. Okay, so we have solved this problem and found the acceleration. So the question I have for you, why do we study the inclined plane so much? And just to drive the point home here, although it's very clear from there that once you set ky equals to 0 in the y component of the equation, what you get is that the normal force is equal to mg cosine of theta. Okay, another case where normal force is not equal to the weight. Somebody just asked. Okay, but I want to come back. Why do we really solve this inclined plane so much in our physics courses? Any ideas?
क्योंकि सर रियल वर्ल्ड एग्जांपल के अंदर सारी सरफेस स्ट्रेट तो नहीं होती.
Yes, but it has something more interesting. It is intermediate
components
case.
find करने के लिए.
नहीं यहाँ वो भी है, ठीक है, but it has another interesting aspect. Okay, it's an intermediate case between two extremes that we are all too familiar. Okay, and those two extremes are and those two extremes are when you have theta equal to 0, you get a flat surface. Okay, and when you have theta equal to 90, then what do you have? Free fall. So this inclined plane gives you an intermediate situation between two extremes, and you should use that knowledge, that understanding to test your answer. That is what I mean by sanity tests. Okay, now if I input theta equals to 0 in my answer, okay, that would mean a flat surface, right? And no acceleration for the block. So now let's see if I get that from my equation. Well, I do. Sine 0 is 0. So the acceleration would be 0. Now substitute theta equals to 90 degrees. Okay. Substitute it here. Sine 90 is 1. And AX is simply equals to the acceleration under gravity. See this? So we have recovered both extreme cases. It means our answer is correct. Okay. Another important point. Now let's say that you're not pushing. Okay. You're not pushing this object. There is no other force. It's just an object sliding down, even if the friction is present and weight, and that's it. All this. What are the possible values of acceleration that you can get for an inclined plane? You cannot go outside this bound unless there is another force present. Okay. The value of the numerical value of your acceleration would be always between this bound. Can be 0. That means if a flat surface, and it can be exactly g. That means free fall. And any other case, any other value, even if the friction is present, because friction opposes. So anything, it is going to reduce the acceleration. So your acceleration is always within this limit. So you're solving a problem of an inclined plane, and you see there is no force acting on your object, no additional push, for example, is not there. And you get an answer which says 20 meters per second. Well, this should raise a flag. Okay, this should ring a bell. This cannot be true because you're exceeding the gravitational acceleration. You're exceeding the extreme case of free fall. Okay? However, the acceleration can be larger than g if somebody is pushing on this object, if there is an additional force along that direction or any other force. Okay, this is what I mean by sanity tests, testing your answers against the extreme cases or the known cases. All right. Some people are confused about FK. That is just that there are two types of friction, the static friction and the kinetic friction. So FK is the kinetic force of friction. But don't worry about it. We are not considering it in these problems. That was just a short way to write it.
लेकिन सर हम पढ़ेंगे.
Yes.
सर एन वाई जो है वो माइनस एम जी कॉस थीटा होगा
जी
ना। एन वाई जो है नॉर्मल वो माइनस एम जी कॉस थीटा होगा ना, क्योंकि वो ऑपोजिट लग रहा है उसके।
NEY minus mg cosine theta. That's what I have it here.
लेकिन जब हम वो जीरो हो गया, अगर राइट साइड वाला एक्सप्रेशन हम जब इसको उधर लेके जाएंगे तो ये माइनस साइन खत्म हो जाएगा ना। एन वाई इज इक्वल टू एम जी कॉस थीटा आ जाएगा।
जी जी बिल्कुल ठीक है।
यस हाँ जी ठीक, थैंक यू।
All right, another example. Any questions so far? All right. So now let's say that we have another situation, another flat surface. Now we have two objects sitting on it, two blocks. Okay, M1 and M2. Okay. Again, we are assuming that the force of friction is negligible, and we are applying a force. We are pushing on this block on the left side with a force F. Okay, and we are interested in what is the acceleration of the blocks. Okay, so the question that we want to answer is, want to find the acceleration. We are pushing the two blocks with the force F. Now we have two objects that we are looking at, and we have to make two free body diagrams, and then we have to look at the forces that is acting on each of those objects. Okay, so two free body diagrams. Coordinate system in this case is simple, y and x. So now let's consider block one, the first block. One of the force acting on the block is the push that we are exerting, F, rightwards. Okay. Another familiar force is its weight, weighing it down, mass times the gravitational acceleration, m1g. Right. Now there would be a normal force. Let's call it N1. Okay, acting on this object. But when you push on this block, and then this block pushes on this block, there would be a normal force acting on block 2 from block 1, but that's not what we are interested in right now, because we are interested in this block at the moment. So there would be a normal force acting on block 1 from block 2, and that we represent with N2 or N3, N2. All right, so four forces are acting on this object, the first block: the push, the weight, the normal force upwards, and the normal force leftwards. Okay. Now we go to the second object. Again, its weight, right? And a normal force upwards, let's call it N3, and a normal force rightwards, we call it N4. This force, the one that M1 is exerting on M2. Okay, only three forces are acting on this block, four forces are acting on this block. Right? Any confusion about this?
सर एक और फोर्स भी तो होगी जो जो एफ है, वो भी तो M2 पे नहीं होएगी?
नहीं,
वो
M2 पे,
नॉर्मल नहीं, आई गेस।
वो M2 M1 पे ये एक्ट कर रही है F, ठीक है। M2 पे सिर्फ N4 लग रही है, वो
बट
जो
आई गेस वो भी थोड़ी सी उसमें फील होएगी, N4 के अंदर इंक्लूड होएगी थोड़ी सी.
Well, let's find that out, okay? More systematically. Okay. Now we start with our vector equation. Sum of all forces equals acceleration, and we consider the case for the first block and only the x direction, because there is no motion in y direction, okay? So that's a given. So if we just focus on the x direction, F acting along x-axis, so positive F, N2, F is positive because this is the x-axis, x direction. So F minus N2, right? And that would be equal to M1 AX, acceleration in the x direction. Okay. Now let's write the same equation for this object. Okay. There is only one force acting along x-axis. N4 equals M2 AX. Okay. Now there is no reason for these accelerations to be automatically equal. So let me just add a subscript or superscript A1x and A2x, the acceleration of the block 1 along x-axis and the acceleration of the block 2 along x-axis. All right. Now if you carefully look, that the N4 and N2 is the action reaction pair. Okay. N4 is the force that M1 exerts on this block, and N2 is the force that this block exerts back on this. So this is Newton's third law, okay? And these forces, although acting on an opposite direction and on two different bodies, they are not acting on the same object. N2 is, you have to be careful with this, okay? N2 is acting on M1. This is acting on M1 in this direction, okay? And N4 is acting on this object in this direction. But the Newton's third law says that their magnitude is equal. Okay, so we can write N2 is equal to N4, that their magnitudes are equal, and we can call it a normal force N. So it's the same for both of the objects. Now, if you rewrite these two equations, okay, I'm just not going to rewrite, I'm just erasing this N2 and N4 and plug N in here. And then add these equations. And before you do that, we also make another assumption that both blocks are moving together. It is not that the one block is moving ahead or faster and the other block is moving behind. They both are moving together. That means that they have the same acceleration. Okay. After making these two simplifications, what we get is you add these equations, you get F is equal to M1AX plus M2AX. Okay. And then if you rearrange this equation, you will get AX is equal to F over M1 M2. This looks like a trivial result, but it's not. Okay. It is not, because if you imagine the two blocks as just one block, okay, and add their masses M1, M2 and replace it with capital M, exactly the same equation that you get. Okay. So we get this result using the Newton's third law, and we can treat the two blocks, the motion of the two blocks, as if it is just one body. And this would not be possible without Newton's third law, and it has some very important implications. Okay, we will realize when we do more examples. So although we were applying the force on the first object, but it is the same as if we are applying the force on the whole object. Any questions so far?
Sir, why do they have same acceleration?
They don't have to. It's just that something we assume that they are moving together. If two objects are moving together, that they would have the same acceleration. If you are in an elevator, your acceleration is, and then the elevator is accelerating, your acceleration is the same as the elevator. But they don't have to
Got
always.
okay, sir, got it.
Okay. Now let's introduce another example and another type of force, if you like, the spring force. Spring force is another type of contact force, if you like. Okay, so you have seen this example a lot, that we have a mass spring system. We have a spring, and then there is a block attached to this spring. So let's say that this is x-axis, right? Now springs are very special objects. They have a natural length, and they really like to maintain it. So if you push a spring from its natural length, you would have reduced its length from its natural length. So it tries to, and then if you release it, it would try to quickly restore its natural length. And if you stretch a spring, so you have actually pulled it further than its natural length, it would try to go back and restore its natural length. And in the process, what the springs do is they exert a spring force that emerges from this property. Okay, and is usually, so let's say that this is the natural length, this position x naught, or let's say that this is the 0 of our coordinate system. Okay, now if you push the object in this direction, the spring would try to pull it backwards. Okay, so if I can write the Fs, the spring force is always in the opposite direction of the displacement from the natural length. So if this is the natural position or natural length of the spring, if you push it this way, it exerts force towards the point where it is coming from. And if you compress it, if you push the block on this direction, so it would exert the force in this direction. Okay, Fs in this direction. So it's always in the opposite direction of the displacement. And the second aspect is that if these displacements from this natural position, or sometimes also referred as the mean position or the average position. So this mean position, if you're not too far away, because once you go too far away, then the things become more complicated. If this compression is not too much, you're not completely pushing the spring up to here or not stretching it, that it actually, in fact, if you stretch the spring too much, it never comes back because the material just yields and its internal structure changes. So as long as you're in the very close vicinity, then the force, the spring force, this obeys this law, which is called the Hooke's law in one dimension, just minus kx. Okay, and k is the spring constant with units newtons per, anyone? Newtons per meter? Yes. Okay, so the minus sign indicates that if x is positive, if x is in that direction, force is in the negative direction. And if the x is negative direction, the force is in the positive direction, and it is linearly proportional to the displacement. The larger the displacement, the larger the force, but within a certain limit. Because if you keep pulling the spring, this law, once you go sufficiently further away from the mean position, this law would be first violated, and then at some point the spring would just break. Okay, and this is called Hooke's law, after a British physicist by the name of Robert Hooke. He was a contemporary of Newton and also his rival. Okay. So now let's say that you are in an elevator, okay? Or let's say that we have an object which is in an elevator. And there is a spring, and on top of the spring is a block of mass m. Okay, and the elevator is accelerating with an acceleration, a fixed acceleration a. Now, what are the forces that are acting on the block? The force of gravity, mg. Now, the force weighs down the spring. It means it compresses it. Okay? If you remove the block, the spring would be at its natural length. Once you place the block, even if the accelerator is not moving, it would compress it, right? It is just like when you stand on a, let's say, a mattress gets compressed, okay? And then spring tries to restore it with its spring force, Fs, in the opposite direction. And the whole thing is accelerating. The elevator is accelerating with acceleration a. So we write the vector equation again. Sum of all forces. So we get minus mg plus Fs. The spring force is in the opposite direction. Fs equals ma. And now we know that the spring force is nothing but kx. Okay. And the displacement would be simply by, the displacement from the mean position would be simply m a plus g over k. But I shortened it. What I want to convey here is that kx is equal to mg plus ma, exactly like the normal equation. Sorry, the normal force. The spring force, which is trying to restore its position, has not only it is not only have to support the weight, but also provide the extra push to counter the acceleration.
सर माइनस के
okay.
एक्स नहीं होना चाहिए.
इनफैक्ट के वाई होना चाहिए यहाँ पे, ठीक है, depending on how you choose the coordinate system. And then
सर
then
के वाई जो है
because
उसको
ky
नेगेटिव नहीं होना चाहिए.
जी जी के वाई जो है वो नेगेटिव है और फोर्स जो है वो पॉजिटिव है ना, ठीक है. तो ये ना मैंने y की वैल्यू यहाँ पॉजिटिव ले ली है, ठीक है. So assuming that y is positive, then you will get a positive sign in here, okay? Because the fs is pointing in this direction. See this, fs is pointing upwards, and fs is equal to minus ky in this case. Okay. And when you actually introduce the displacement किस डायरेक्शन में, नीचे की तरफ है ना, इस डायरेक्शन में है ना, ठीक है। तो अगर आप मैं y की वैल्यू पॉजिटिव ले लूं और इसका जो नेगेटिव है वो बाहर ले आऊं तो ये kx नहीं हो जाएगा, ky नहीं हो जाएगा। In this particular case, because y is negative, ठीक है। अब I have chosen a y, I've made y to be positive number, okay, and there is a minus sign with this y value, ठीक है। तो इसलिए ये साइन ठीक है, otherwise you're right. So this is the force that is acting. These are the forces that are acting on the block. But now we want to analyze the forces that are acting on the spring. Okay. Okay, so now we have the spring and the block, okay, which is weighing it down. And then we have the floor of the elevator. Okay, if I want to write the free body diagram of the spring, there is weight of the spring, MSG, okay, that is weighing it down. Then the spring exerts a force Fs on the block, okay, and the block exerts a force minus Fs on the spring. So there is another force acting on the spring, minus Fs in this direction. Okay, this is also minus mg minus Fs. And if these were the only two forces, then the spring would just collapse and go through the floor of the elevator. So there is a normal force that the floor of the elevator is exerting on the spring. Okay, we call this F. Okay, all three forces, if you put together, you can write F minus Fs minus MSG equals MSAS. Right? So it is very practical for the problems that we would do, and is usually the case that we consider that the spring has very, very small mass. We always assume that it's a massless spring. So this is an approximation to simplify the problem, okay? So we assume that MS is very, very small, close to zero. That means that gives us a license to just ignore the weight of the spring in this equation. Okay, we can't ignore this term because AS can be anything. AS can be large. Okay, but G is a fixed number. A fixed number G10, number 10, like value 10 meters per second square multiplied by a very, very small value. This definitely gives us a small term. This is not small. Okay, can be very large. So the equation simplifies to F minus Fs equals MS AS. And from here, you can find the acceleration of the spring. AS is F minus Fs over Ms. Now we also know that the elevator is going upwards with an acceleration A. Okay, so this is equal to A. But if ms is very, very small, okay, for this acceleration to be finite, the only possibility we have is that these forces are equal. The downward force by the block on the spring is equal to the normal force exerted by the floor, okay, exerted by the floor of the elevator.
सर
Yes.
प्लीज आप ये दोबारा समझा सकते हैं, मुझे सही समझ नहीं आया.
Because if we are taking the spring to be massless, so if we are sending mass to zero, ms to zero, the acceleration would be infinite.
सही है.
The only possibility that this acceleration can be finite, okay, for is if the upper term is zero. If f
Sorry.
minus fs is zero, which means f is equal to fs.
सर इसके अंदर जो F है वो बेसिकली क्या है?
F जो normal force है, floor of the elevator is exerting on the spring.
अच्छा.
Right?
और सर आपने ये क्यों अज्यूम किया कि जो एक्सेलरेशन ऑफ स्प्रिंग है वही एक्सेलरेशन ऑफ एलिवेटर भी होगी?
वो इसलिए क्योंकि they are attached to each other, okay,
अच्छा.
and they're moving together.
अच्छा.
Okay, and fs here in this equation is the force. So you see the block. So this is the situation. So you have we have few minutes. Okay, so you have the spring here. This is the floor of the elevator. You have the block. Okay, once you put the block pushes the spring down. Let's say the elevator is stationary, not moving. The block pushes it down, and now you get a new situation where the length of the spring is compressed from the natural length a little bit. Okay, exactly equal to what the weight of the spring does. Now spring is exerting a restoring force on the block, Fs on the block, and the block is also experiencing weight. So those are the forces acting on the block. What are the forces acting on the spring? The spring, one is this force, the ceiling, the floor, because if the floor was not exerting any force, then the spring would drop through. So there is a force coming from the floor of the elevator, and the spring is exerting a force Fs on the block. Okay? So the block is exerting the same force on this block Fs, okay? A reaction force. So now spring has two forces, and the third force is the weight of the spring itself. So that's what the three forces I have here. The normal force from the floor of the elevator, the spring force, which is being exerted by the block on the spring, and the weight of the spring equals to the acceleration term. And then we just ignore, we say that the mass of the spring is very small, and I'll show it in a minute why we can ignore it and how. Well, I will try to rationalize it in a minute, okay? But for the acceleration to be finite, the force that the block is exerting on the spring and the force that the elevator is exerting on the spring, those two forces, they're not directly related to each other. They are not action-reaction pair. Both are being exerted by two different bodies on the same object, and they become equal not because of the Newton's third law. This is very important. They become equal because of this assumption that I assumed that the spring is massless. Otherwise, these two forces would not be equal, and this is not action-reaction pair. One force is being exerted by the block on the spring, and the other force is being exerted by the elevator on the spring. Two different bodies exerting two forces on the same object from two different sides, and they become equal only because of this assumption.
तो सर अगर F equals to Fs होगा तो फिर एक्सेलरेशन 0 हो जाएगी ना?
Acceleration फिर वही होगी ना जो elevator की होगी, तो है ना F.
नहीं,
Equal
अगर
to
F
Fs.
equals to Fs है तो फिर F minus Fs equals to 0 हो जाएगा, और फिर consequently A भी equals to 0 हो जाएगा.
वो ये acceleration 0 हो जाएगा. उसका जो है जो spring का acceleration है.
स्प्रिंग और एलिवेटर की सेम ही एक्सेलरेशन है ना, तो अगर दोनों में से एक भी 0 हो गई तो दोनों ही 0 हो जाएंगी ना?
हाँ जी, मुझे समझ आ रही है आप कंफ्यूजन. It will become clear in a minute, okay? So the point is that this is not, so this is the acceleration would become infinite because mass is 0.
सही है
ठीक है ना? So for this equation to make sense, the only possibility we have is for the spring is that this upper, the denominator in this equation is 0. Okay, it will become clear in a minute. Okay. So now we have the situation that the spring, the force that the spring is exerting on the block Fs minus the weight of the block mg equals ma. Okay. And this is the equation for the block, and I'm writing the equation for the spring. F minus Fs minus msg equals msa. Okay. Now let's add these two equations. Okay. This term would cancel, and you will get F minus msg plus or minus mg equals m plus ms times a. Okay. And from here, you can, from this equation, you can get the acceleration in terms of everything else. F minus msg minus mg over m plus ms. Okay. From both the numerator and the denominator, please take m to be common. Okay. And you would get, and then if you take it common, that it cancels with each other. So you would get an equation which looks like F over m minus ms over m times g minus g over 1 plus ms over m. And by taking common, I mean if you have m here and m here, and these two just cancel. Okay. Now you look at this equation and look at these two terms. So why we are taking a massless spring is that the general situations which we are dealing with, the mass of the objects that we are interested in, for example, the block in this case has this mass, and this fraction appears in the equation. So what usually we have is that the mass of the objects we are dealing with is much, much larger than the mass of the spring. It's so large that we can simply, this fraction, we can simply ignore this term. Okay. We can simply ignore this term. It's the ratio of the objects, the masses of the objects involved with the mass of the spring. Okay. If you take this limit, you will get the acceleration equals F over m minus g. Okay. You see that the acceleration is not 0.
सर आप एक दफा
और
दोबारा बता दीजिए आपने इनको कैंसिल आउट किस तरह किया?
Okay. किस चीज को कैंसिल आउट, इसको या इसको?
ये जो आपने इक्वेशन एंड में फॉर्म की है f over m minus g, ये आपने पिछली इक्वेशन से किस तरह यहाँ पर आए हैं वो पूछ।
देखें ये ना, इसमें अब मैंने ये कॉमन लेना तो समझ आ गया ना बोथ टर्म से।
जी वो तो समझ आ गया।
अब मैं ये देख रहे हैं कि we have a very small number ms. I'm saying ms is very small compared to the bodies that we are dealing with, जो उनकी masses हैं ना, ठीक है ना?
सही है।
तो इनकी जो if you divide a very small number, let's say, by a very, very large number, so what do you get?
Very
And-
close to 0.
Very close to 0, an even smaller number. So that's why I'm saying that these terms we can ignore. They're insignificant, okay? So just ignore this term and also ignore this term. So the rest of the equation is written there. A is equal to F over M minus G. नीचे तो 1 बचा है, कुछ भी नहीं बचा. All right? And now from A is equal to F over M minus G, I can write F minus mg is equal to ma. So the force that is causing the acceleration is the difference between the force upwards and the gravitational pull. That the difference of these two forces, as it should, is equal to the acceleration of the elevator. But then we are also saying, so look at this here, and then we are also saying that the force F is equal to Fs. So I can write another equation. Fs minus mg is equal to ma. Well, this is possible only if F is equal to Fs. And the whole point of this whole exercise is and let me say it very slowly, is this, that if you have a massless spring, you have a perfect transmission of the force. Okay? If you have a perfectly massless spring, you have a perfect transmission of force. What that means is that if the spring is massless, whatever force you are exerting on this end of the spring would transmit it up to the block without any changes to the force. Okay? And this has nothing to do with Newton's second law or third law. Okay? This is because we're assuming the spring to be massless. So it's a perfect transmission that when we will be dealing with the problems where we have ropes or we have springs, and sometimes you read in the problem statements that the rope is elastic or is non-stretchable. All those special cases or all those warnings are to give you an idea that there is a perfect transmission of the force. Okay, so assuming that the spring is massless, whatever force you exert on this end of the spring, it's exerted on the other end. The spring exerts the same force on the object on the other end of the spring. Okay, that is the whole point of showing this. The force for a massless spring, the force exerted by the floor of the elevator is equal to the force exerted by the spring on the block. And with this, thank you very much.
Sir, I wanted